Hi everyone, in this video we will try to prove the formula for second order differential equations when discriminant is less than 0. First of all, let's start with the case when discriminant is greater than 0, and then we will just continue with the case, opposite case. And let's start, for example, if we consider that our differential equation is d squared y divided by dx squared plus 5 dy dx plus 6y is equal to 0, and we will consider in this example only homogeneous cases when our differential equation will be equal to 0, then not any other function will be in the right hand side of our equation. And here we should, in order to find the solution, we should call y e to the power kx, because each time when we find the derivative of e to the power x, we get the same result, and only different variable here will be the power of k, because when we find derivative, the k will come here. And for example, let's just write here k e to the power kx. And again, if we want to find the second order derivative, it will be again k squared e to the power kx. And let's just put this value into our equation and try to find the solution. First of all, the second derivative, which we found k squared multiplied by e to the power kx, plus the first order derivative k 5 multiplied by k multiplied by e to the power kx, plus 6 multiplied by e to the power kx, because it's just our y value. And this will be equal to 0. Let's put our e to the power kx value term out of the brackets, and k squared plus 5k plus 6 is equal to 0. This is never going to be 0, and therefore this term here should be equal to 0. And let's just write in terms of the two terms multiplication, k plus 2 multiplied by k plus 3, and this will be equal to 0. k1 is equal to minus 2, k2 is equal to minus 3, and we found our roots. And at the starting point, we thought that y is equal to e to the power kx, which means that our, for example, first solution e to the power minus 2x, and we can multiply it with any constant because it will be just unchangeable throughout the derivation, and will not affect the final result, because when we did multiply c1 0, it will give us 0 every time, and therefore c1. Second, for example, our solution is c2, again for the same reason, to the power minus 3x. And let's just think that if we just sum up these two terms, this will be our solution again, because when you find d squared y dx squared, second derivative of y function with respect to x, you can just divide these two terms into two parts. For example, you can write the fx plus gx divided by dx. This is equal to dfx divided by dx plus dgx divided by dx. Therefore, because of the same reason that can be applied here, our final solution will be c1 multiplied by e to the power 2x minus 2x plus c2 multiplied by e to the power minus 3x. And using the same condition, we will try to prove our theorem for just case when you find here, for example, discriminant. I didn't find, I just wrote this way. But when you find discriminant, you can get the roots again, and when you find it, discriminant is equal to, it is 5 squared 25 minus 4 multiplied by 6 multiplied by 1, which is equal to 1, which means that discriminant is greater than 0. But in other cases it can be something else. Now let's just consider the case when our discriminant is less than 0. Almost the procedures that will be followed here in the second part of the video will be the same as the first part. Let's just write sample and see what's going to happen. For example, d square y divided by dx square plus 16y is equal to 0. And let's just put y is equal to e to the power kx. This will be k square e to the power kx plus 16 times e to the power kx will be equal to 0. Let's just cancel off these terms and we will see that k squared is equal to minus 16. As you see, in this part, discriminant is less than 0. We cannot find the real solutions. Therefore, we will just use complex numbers here. Square root 16 y squared. And this is plus minus 4y, 4k. And as you know that each complex number can be represented in terms of p plus minus 2. And here you see the p-value in this sample is equal to 0. Therefore, in the solution C1 e to the power lambda 1 solution 1 t plus C2 e to the power lambda 2t, which are the roots of our equation. We will not use this part because we just want to generalize the formula, therefore this value will be used. And let's start. Let's just put this value into equation. C1 multiplied by e to the power p plus q p plus qi t plus c2 multiplied by e to the power p minus qi t. This is the final solution. Let's just take e to the power pt out of the brackets. C1 e to the power qit plus c2 multiplied by e to the power minus qit. And in order to just simplify this one, we will use Euler formula which states that e to the power I phi is equal to I sine phi plus cosine phi. And here just the only changing variable will be the q and t. Let's just write this ones. I will be the same, e to the power pt multiplied by c1, and apply this function, Euler's formula. Let's just put it in the box. It will be just I sine qt. Our angle here is qt multiplied by phi is equal to qt, and I is the same. Sine qt plus just cosine qt. It is just a little bit not neatly, and let's just write plus c2 multiplied by and all the q terms we just put minus sign and get the final term for this part. It will be I sine minus qt plus cosine minus qt. And let's just simplify this one, e to the power pt multiplied by and c1 multiplied by I, and this term here can be written that minus c sine qt, because when you know that if we just draw the axes, the x and y axes, so that the minus 1 means that minus degree here, and our sign values depend on just y-axis. It will be minus, therefore our value will be minus negative term, and we can write it in terms of here with the help of same angle, but we should put the minus sign to the front of the term here. And let's just write it. It will be equal to c1 multiplied by I sine qt plus cosine qt, and put it here, e to the pt, first part, and second part, c2 minus I sine qt plus, and for cosine minus qt, it will depend on the x values, and x value is not changing when we just go through minus angle and positive angle here. Therefore it will be the same as cosine qt. And for the simplify it, we will put the same terms into brackets for pt multiplied by c1 minus c2 multiplied by I sine qt plus c1 plus c2 cosine qt. And this is also constant. We can write it with the help of a1, and this is also constant a2. And here a1 can replace both c1 minus c2 multiplied by I, because these are constant terms. E to the power pt multiplied by a1 sine qt plus a2 cosine qt. And this is the simplified final formula for the second order differential equations when the discriminant is less than 0, and you can just find the roots, and if they are represented in terms of complex numbers, just put the values into the equation and find the solutions for the case. And this is the end of the video. Thank you for watching. Please like, comment and subscribe to my channel.